Hello everyone. So today we'll be discussing upon dynamic force analysis. So let us first see what a dynamic force analysis is. So earlier we saw static force analysis. So what is different from static force analysis over here is, here in dynamic force analysis we are also considering inertia forces that are occurring in the system. So whenever any force is getting applied, that force is equal to mass into acceleration, right? So whenever a force is getting applied, we are taking into account the inertia force also. What is inertia force? Inertia force is the force required to bring a body into equilibrium when it is accelerating. So suppose if a body is there, so if you have a body and it is having an accelerating force, right? Accelerating force, it is accelerating with an acceleration of a, body's mass is m. So then inertia force Fi is equal to ma. It is nothing but the force required in the opposite direction to bring the body in equilibrium, into equilibrium, that is to bring it to a standstill. So that is what is called as an inertia force. Now this principle is called as D'Alembert's principle. So as per D'Alembert's principle, inertia force is the entity that brings the moving body with an accelerating force into equilibrium. So that is the first concept that we need to understand in dynamic force analysis. So we are going to take into consideration mass and acceleration. So together inertia forces, inertia torque and inertia couple, such quantities come into picture over here in dynamic force analysis. So what we are basically going to do over here in a dynamic force analysis problem is, you will be given a system, that is a 4-bar chain or a slider crank chain, and you have to first draw the velocity diagram, then the acceleration diagram, and so with that you are finding out the acceleration of each of the links. And with that, you are finding out inertia forces, and then you are finding out the forces that are acting on the links, and thereby you are converting the system, your dynamic force analysis system, into a static force system. So here also a part of the problem is static force analysis, which we have already covered in the previous video. However, I'll try to recap at the end of it in a brief way. In a quick way. So if in detail you want to go into static force analysis, already uploaded videos are there previously, that also you can refer. Okay, so we'll start with dynamic force analysis for today. So this principle is called as D'Alembert's principle. Okay, D'Alembert's principle. What is D'Alembert's principle? I'll tell you the gist of it. Whenever a body is moving at an accelerating force, F, you can call the accelerating force as F, then it can be brought to an equilibrium by applying an inertia force. Okay, which inertia force is Fi. Now, if there is a inertia couple also in acting on the body. Suppose, let us see, I have an inertia couple acting on the body. So, inertia couple and an inertia force. This is a body of mass m. I have an inertia force acting over here and also an inertia couple. Right, inertia couple also, suppose it is of the same value as that of your Fi. Let us assume that inertia couple also, so what is a couple? Couple is force into perpendicular distance, right? So here you have two equal and opposite forces acting on the body, which constitutes a couple. So suppose this Fi, value of Fi and magnitude of Fi and magnitude of the forces which are causing the couple are equal in magnitude, then then what happens? Then you can actually cancel out these two forces, right? This is also an Fi, this is also an Fi. So these two gets cancelled out. So in short, what happened here? Fi, which was initially over there, it got shifted by a perpendicular distance, right? It got shifted by a perpendicular distance over here, right? So when you have an inertia couple, and that is a couple and a force that are acting on the body, you can actually shift the force with a perpendicular distance. Okay, that is the concept that you have to understand. Let us discuss a dynamic force analysis problem. That is a method how to do the problem when you get one in dynamic force analysis. That is, I'll be very specific, because I'm not going into extent of to cover all the topics, because it is literally not possible for me to maybe in a 20 minutes or 30 minutes video to cover all the concepts of dynamic force analysis. However, I'll try to explain everything that is useful for you, or that is needed for you. So when you get a dynamic force analysis problem, so this is a dynamic force analysis for a 4-bar chain. Let us start with a 4-bar chain. So you have a 4-bar chain given in the problem. Now here, what is different from the earlier problems that we have is, you will be given center of gravity, that is G2 and G3 and G4, let's call it like that, G2, G3 and G4, that is for the second link, third and fourth link respectively. This is my first link, this is second link, third link and fourth link. So correspondingly I am naming G2, G3 and G4, that is the center of gravity. Along with that, you will also be given in the question, we also need M masses, M2 of this link, and similarly M3 of, that is the mass of connecting rod, similarly the mass of the fourth link. So all these masses will be required to you. Along with that, you will also be required omega. So this is omega 2, and here you will be having an alpha, which is your angular acceleration, that is alpha 3, and here you will have an alpha 4. So what all things should be given over here in the question? You should be given your masses of each of the links. You should also be given the center of gravity, where the center of gravity is acting on each of the link, and alpha and alpha's direction is also important. So alpha's direction should also be given in the question. So that is the start. This much values we will need for starting the dynamic force analysis problem. Now let us see, what is our first step? Our first step is always drawing the configuration diagram. So draw the configuration diagram as per scale. Okay, the measurements will already be given. You just have to draw it in paper. Now once that is done, you will need to draw your velocity diagram and acceleration diagram. So this velocity and acceleration diagram we have studied in kinematics of machines, that is mostly in all the engineering colleges. It is handled in 4th semester under relative velocity and acceleration method. You are studying how to draw a velocity diagram and acceleration diagram. However, I can understand that many of you may not remember velocity and acceleration diagram. So we will be doing that first. From that, so usually students tend to take around 20 minutes time to draw the velocity acceleration diagram. After that, again another 20 minutes for your static force analysis problem to solve it. So here, so together it will maybe, if you are very good, you will at least take 30 minutes to solve this problem. So make sure that you practice this very well at home. then only it will be possible for you to attempt it in a fast way. So let us get on with it. So here, while drawing the velocity diagram, let us first draw the velocity diagram. So first thing that we need to understand is the velocity components are always acting perpendicular to the links. So you have a velocity component. Now I'm going to erase all these extra things that I have written over there on the sides, because we'll be needing, I'll be needing you to show the velocity components and acceleration components. Right, so this is my link 2, this is 3, and this is 4. So suppose I take the velocity for my link 2, it will always be acting perpendicular to the link. That is, this is A, B, C and D, right? So here, this velocity is velocity of B with respect to A. Velocity of B with respect to A. Now again I am going to consider the velocity of this connecting rod BC. So that also will be perpendicular to the link. So this is the velocity of BC. Let us see. This is also perpendicular to the link. This is velocity of B with respect to C. Now I have not marked the direction. Okay, I have not marked the direction. So direction, I will tell you how we will come to know. Now this is velocity of B with respect to C. So this is relative velocity method. So in relative velocity method, you always compare velocity of one point with respect to another. So that is a relative velocity. So this is velocity of B with respect to C. I can also draw velocity of C with respect to B. That is also fine. It is also correct. So as we go forward, you will come to know how it will differ. Okay. So now this is velocity. This is also perpendicular. This is velocity of C with respect to D. So you have 3 velocity components over here. And since one is a fixed link, we are not considering that one. So the second link, third link and fourth link have their velocity component. So I have marked this one in green, red and blue, so that it will be easier for you to identify. Now, velocity of B with respect to A, we are starting from one point. We are considering any one point over here. Let us name this point as A, D. Now, why are we naming it as A, D? Because A and D are the fixed points. We have to always start velocity and acceleration diagram from the fixed points. Okay, so this is A, D. Now, I'm going to draw VBA parallel to this one over here. Right, VBA parallel to this. Now, what is the value of VBA? I need something, no? I need a scale in order to draw this one. Right, so in order to get the scale, I want VBA. What is the value of VBA? VBA is equal to what? Omega into R. Omega into R. You have studied this formula, right? Linear velocity is equal to omega into this angular velocity into radius. So here omega is nothing but omega of the link AB, and R is nothing but the length of the link AB. Right? So I'll be getting omega was already given in the question. So I know omega AB I can measure from here. So I get the value of VBA. Once I get the value of VBA, I'm converting it into a scale and then I'm drawing it. Right. So here I'm drawing VBA first and I'm taking a particular scale. Okay, so scale is what you are getting it in meter per second. So here I have to convert meter per second equivalent to a distance, right? So equivalent to mm. So I have to consider mm in terms of no, meter per second in terms of mm, right? So that is conversion into the scales. Now again VBC. Again I'll need VBC as well as VCD. Right. Now VBC and VCD I'll need. Now even if these values are not available, you can get it from, you just need one value because the other two you will be getting now. So let us see, I'll just once again draw velocity diagram. So as per a suitable scale, I'm starting from A, D. Parallel to this, I'm drawing VBA as per a scale, as per any suitable scale, right? Now once that is, now I have not marked the direction yet. Okay, now what is this end over here? Here I already have A. Now this is VBA, so this end is going to be B, small letter b. Okay, B. So this is VBA, so the velocity's direction will be towards B. This velocity of B with respect to A, so the velocity will be towards B. Okay, always remember that one. So if it was velocity of AB, that is velocity of A with respect to B, then the direction would have been acting downwards towards A. Okay, I hope it is clear. Now let us move on. We have to take VBC from here, VBC from here and VCD from here. So is that B over here? No, this is A and D. B is there over here. So let us take, this is VBA. Right. So velocity of BC. I don't know the magnitude of velocity of BC. Okay, I'm drawing parallel to this. I'm drawing over here. This is what? VBC. Right. Now I don't know the magnitude, so I'm just simply drawing a line. Now what am I left with? VCD. VCD. That also the magnitude I'm not knowing. So I don't know. So I take it from here. CD, right? So D is there over here. C I don't know yet. So parallel to this, I'm drawing over here. So here I am getting VCD. Right, now we have to find out the direction. How to find out the direction? This is velocity of C with respect to D. So here, this point is C that we obtained just now, right? This is BC and CD together join here for C. So here this is VCD, so I'm marking it towards C. This is velocity of BC, so I'm marking it towards B. Okay, now so this is your velocity diagram. So here from here you can measure VBC and convert it back into the scale that we have taken. So that we will be getting a definite value for VBC and VCD. We will be definitely getting a value, a magnitude we will be obtaining from here. So we got your magnitude and direction also for all the velocity components. Now comes the acceleration diagram. The next part is acceleration diagram. So let us see how to draw the acceleration diagram. Now here also you will require a scale. Okay, you have to, because whatever is you are getting in meter per second square, you have to convert it into a mm, right? So a suitable scale is required. Now while drawing the acceleration diagram, we again need the magnitude of each of the acceleration component, right? So coming to acceleration components, every link has two acceleration components. Okay, so here suppose if I take AB has two acceleration components, that is ARAB and ATAB. ARAB is going to be parallel to the link, and ATAB is perpendicular to the link. Okay, this is parallel to link and this is perpendicular to link. Okay. Now, similarly, I have for BC and CD. So BC is having again ARBC, ATBC. Here also I have ARCD, ATCD. Now acceleration is the only thing that you have to take care over here. Suppose if in the question, when at the start of the question, if it is given that the crank is rotating or any one link is rotating at uniform velocity or at constant speed, then your tangential component will become 0. Okay, what is it? If in the question it is given that alpha is 0 or your it is rotating at a constant velocity or constant speed, then your AT will happen to be 0. So here, over here in this question, there is a possibility, because in order to start the problem, we will need the value of ATAB. Okay, otherwise we can't start the problem. Okay, you have to think it in this way. That is what I'm telling you. So in order to start the problem, you need the value of ATAB. So either this AB's alpha value should be given to you, or it should be given in the question that it is rotating at a constant speed or constant velocity. So if in the question it is not given, the alpha value is not given or the constant velocity is not given, then you can assume that the link AB is rotating at a constant velocity, and thus you will have your ATAB getting reduced to 0. Okay, so always ATAB gets reduced to 0 whenever your link is rotating at a constant velocity. Always remember that. So here in this case, your ATAB is going to be 0 because we are assuming that it is rotating at a constant velocity. Now ARAB is equal to V square AB divided by AB. AT is alpha into AB. Alpha is nothing but your angular acceleration. Okay, so alpha into AB. So here it is 0. Similarly over here you will have V square AB divided by BC divided by BC. Similarly over here it is alpha into BC. Here also ARV square CD divided by CD, and here it is alpha into CD. So we'll get the values of all of these because we know V square BC, V square CD, and all these values we already know. Okay, so let us see.